So till now, we have seen the geometric interpretation and the probabilistic interpretation and the probabilistic interpretation of logistic regression, right? So there is another interpretation of logistic regression called as the loss minimization interpretation, which is beautiful actually. When I first learned about it, I said, wow, this is a phenomenal way to understand logistic regression itself. So let's understand this. Let's understand this part. Again, going back to our optimization problem is W equals to the argmin of your loss function, right? Log of 1 plus exp of minus yi w transpose xi, right? Now let me call zi as yi w transpose xi. Sometimes it's also written as yi into f of xi. Because what is f of xi? What is f of xi? It's nothing but w transpose xi in logistic regression, right? Your function, your classification function, right? The function that determines whether you're positive class or negative class is nothing but w transpose xi. So some people write this as zi. Some people also write it as yi into f of xi, right? So if they don't want to explicitly say it's logistic regression, it could be any function, right? For logistic regression, it happens to be w transpose xi, right? So this is our optimization problem, and we'll try to arrive at this from a completely different perspective called the loss minimization framework or the loss minimization interpretation. So imagine, forget about all the math till now. If you want to build an ideal optimization function, if you want to build an ideal optimization model for classification, what would you do? You would say something like this. You would say that you want to minimize, you want to find a W, that minimizes the loss. Let me define what loss means. For example, so before we go and write this, let me define what loss is first, right? So imagine if I give a value of +1, if a point is incorrectly classified. If a point is incorrectly classified by my model, right? And I want to give it a value of 0 if it is correctly classified, right? So what I want to minimize, so just imagine for a while that I'm giving a value of +1, right? If my data point xi is incorrectly classified by my model, and I'm giving it a value of 0 if it is correctly classified, then what do I want to minimize? I want to minimize, right? I want to minimize the number of incorrectly classified points, incorrectly classified points. That's what I want to do, right? I want to minimize the number of incorrectly classified points, right? Suppose if I have a function, so again, I have a function. Imagine I have a function that gives +1 for incorrectly classified, 0 for correctly classified. Then I want to see what is the whole objective of classification. What is the whole objective of classification? Find the parameters like W that minimize the number of incorrectly classified points, right? So imagine if I in the case of logistic regression, imagine if my x-axis here is Zi. What is Zi? Zi is yi into W transpose xi, often written as yi into f of xi. All right. So if this is my Zi, how should my loss look like? So this is called as loss, right? You're trying to minimize the loss or maximize the profit, right? We all try to minimize loss or maximize profit, right? If I define my loss function such that, I will give +1 for incorrectly classified and 0 for correctly classified. I want to minimize my loss, or I want to minimize the number of incorrectly classified points, right? So if my loss function, an ideal loss function would do this, right? So how should my loss function look like as Zi changes, right? If Zi is positive, so let's define one loss function, right? This loss function will look like this. If Zi is positive, what does it mean? It means my point is correctly classified. If Zi is positive, remember Zi is yi w transpose xi. If Zi is positive, it means the point is correctly classified because the sign of Yi and W transpose Xi is the same in logistic regression, by the way, in logistic regression, right? Then the loss should be 0 for the ideal loss function. Remember, this is my ideal loss function. This is my ideal loss function, right? So this value will always be 0 when this is 0 again. This is Zi equals to 0. So whenever Zi is positive, the loss function also should be 0. And whenever Zi is negative, which means in this region, right, your loss function should be 1. That's what we defined our ideal loss function to be. Such a loss function where if your loss function is +1 for incorrectly classified points and 0 for correctly classified points, such a loss function is called as the 0-1 loss function. Such a loss function is called the 0-1 loss function. It's almost ideal, right? So if I have a loss function like this, then what am I trying to minimize? I want to find a W star such that argmin of, right, summation over all the points 0-1 loss of Xi. Right, given Xi, Yi and W. Okay, let me write it more carefully. Given Xi, Yi and W, I can compute a 0-1 loss, right? If you give me Xi, Yi and W, I can compute Zi. If you can compute Zi, given this function, what does this function look like? The 0-1 loss function, the 0-1 loss function of Zi equals to 1 if Zi is less than 0. It is 0 if Zi is greater than 0. This is what the 0-1 loss function looks like. So you can look at your ideal system, almost ideal system for optimization from a loss function minimization perspective as finding a W that minimizes the 0-1 loss. And why is it called loss? That's very important because we want to minimize loss and maximize profit, right? Now, this is the ideal loss function, but there's a problem with this ideal loss function. So this loss function here is called the 0-1 loss function. This has a problem. Remember, till now we have written optimization functions like this. We have written optimization functions. We have not solved them. To solve optimization problems in general in machine learning, not always, but in general, to solve optimization problems in machine learning, we will use calculus. We'll use very specifically, we will use differentiation. We'll use differentiation, the simple differentiation that we learned in our 11th grade or 12th grade or undergraduate mathematics. We will use differentiation in calculus to solve these optimization problems. We will see how to solve these optimization problems in the next chapter. Till then, all you have to know is that if a loss function or if an optimization problem is not differentiable, you can't do much about it. I'll tell you why it is so in the next chapter when we learn optimization in more detail, right? So the problem here, if for those of you who remember basics of calculus, a function is differentiable, a function f of x is differentiable. Okay, for a function to be differentiable, first it has to be continuous. It has to be continuous before it is even differentiable. You might remember these terms from your 11th or 12th grade, right? So let me define you what is a continuous function. If this is my Zi, how does my 0-1 loss function look like? My 0-1 loss function will look like this. Now, one thing you'll notice is there is a discontinuity. There is a discontinuity at Zi equals to 0. There is a discontinuity because till the time, see, look at this formulation. 0-1 loss of Zi is equal to 1 if Zi is less than 0. But if Zi is greater than 0, it is 0. But what if Zi equals to 0? When Zi becomes equals to 0, this value can either be 1 or 0. It's not defined actually clearly. The 0-1 loss function is not perfectly defined at Zi equals to 0 because this function is not continuous. And functions which are not continuous are not differentiable. Not continuous implies not differentiable. right? So 0, 1 loss function, even though it is ideal, you can't differentiate it. And since you can't differentiate it, you can't solve the optimization problems in machine learning using 0, 1 loss function. So what people have tried is, people have said, since we can't differentiate 0, 1 loss function, let's try to approximate it. So, right? In lot of optimization and mathematics, if you can't solve a problem, approximate it. Why not? One such approximation is called the logistic loss. Okay, I just Google searched for logistic loss on Google Images, and this is what I got. So what I do often is, whenever I'm not sure, I'll just say logistic loss function. I got this link from Stack Exchange. Very, very nice link. So let me explain what this link means, right? So let me just quickly explain. So this is your yi f of xi. This is your x-axis, which means this is your zi, right? Your loss function is here. Loss function is often written as capital L, right? The y-axis here is the loss function. Is a loss function given yi and f of xi. And f of xi in logistic regression, f of xi in logistic regression is nothing but w transpose xi in logistic regression. Right? So having known this, right? This is your zi, this is your loss, right? Now when loss equals to 0, so this black line that you see here is your 0, 1 loss, as it is mentioned here, right? Because whenever your zi or yi f of xi is positive, it gives you a value of 0. Whenever it is negative, it gives you a value of 1. But this is not continuous because it's suddenly dropping here, right? This is your 0, 1 loss function, this black line, right? So people said this is not differentiable, and we need functions to be differentiable. Which means we need them to be continuous to start with for us to operate in the 0, 1 loss. So they said, since 0, 1 loss is not differentiable, why don't we approximate it? One such approximation is called the logistic loss. You see this red line here? Right? This red line is the logistic loss. This is what you get when you do log of 1 plus exp of minus zi. Okay, I'll prove this to you. I'll just prove this to you quickly, right? So let's actually go to Google, our good friend, log of, okay, I already tried it once. This is exactly what you get, right? If you notice, this is exactly what you have here. Right? So logistic regression. So this is your logistic loss. This is your 0, 1 loss, which is almost the ideal case. But since we can't differentiate it, and since it's not continuous, we are looking at logistic loss. Logistic loss is a very interesting loss. Now you might say, I could have drawn any other function like this, right? Of course, you could have drawn a function like this. Nobody is stopping you from doing it, right? You could have drawn a function like this, if you can find such functions easily, right? Each of them is possible. One such possibility is logistic loss. We are not saying logistic loss is the best one. All that we are saying here is logistic loss is an approximation. What I'm saying here is logistic loss is one approximation of 0, 1 loss. It has some differences, of course. What are the differences? In 0, 1 loss, anything wherever zi is greater than 0, you get a value of 0. But what happens with logistic loss is it's not actually 0 when small values of zi. Only when zi becomes very large, this will tend towards 0. That's one difference, right? Because this red line is not simply falling off like this. This red line is not simply falling off like your 0, 1 loss, right? That's one. Second is on the negative side. So on the positive side, your logistic loss is not exactly equal to 0 for all zi greater than equal to 0. It'll very fast move towards 0, right? As zi becomes more and more positive, it will quickly move towards 0. But as zi becomes negative, like this is the negative region, right? This is the negative region. In the negative region, your 0, 1 loss always gives a value of +1, while your logistic loss function is saying, if a function is misclassified, I'll not always give it a loss of +1. I will give it a loss which is like this. This loss is increasing. Remember, this function, look at the negative side of things, right? This is the positive side of things. Look at the negative side. When your zi is negative, your logistic loss is no more always equals to 1 like your 0, 1 loss function. It increases very, very sharply like this, right? So logistic loss is one approximation to 0, 1 loss. There are many such approximations. When we use logistic loss as an approximation to 0, 1 loss, we get logistic regression. There is another loss called the hinge loss, because this is like a hinge, right? This green line that you see here, which comes till here, and then here it becomes 0, right? This green line that you see, which is falling sharply here, and then it becomes equals to 0 at zi equals to 1. Right? There are many, many functions like this. As I told you, I can draw thousands and thousands of functions like this. I can draw a function like this. I could have drawn a function like this. There are many, many such functions. The most studied are logistic loss and hinge loss. So when we apply hinge loss, what we get is another algorithm in machine learning, a very, very popular algorithm called support vector machines. Right? So what I really love about the loss function interpretation, or this is called the loss minimization interpretation. So what I love about the loss minimization interpretation, what I love with the loss minimization interpretation of any machine learning classification algorithm is, if you just change the loss function slightly, if you have the loss function as logistic loss, what you get is logistic regression. If your loss function is hinge loss, what you get is support vector machines. There are other losses here. There is something called as exponential loss. When we have this, we get an algorithm called as AdaBoost. Right? So there is something called as squared loss, actually. When we use squared loss, we get linear regression. So by just changing the loss function, by changing the form of the loss function, you can learn multiple algorithms in machine learning. That's what I like about loss minimization interpretation, because loss minimization interpretation very gracefully connects various algorithms by putting them into one diagram. If there is one diagram that connects multiple algorithms in machine learning, it will be the loss function interpretation, the loss function diagram. Right? In this single diagram, you can get many, many models. Right? So if you go to Wikipedia, actually, I think this link comes from Wikipedia. Yes. If you go to this link in Wikipedia, right? So this is the blue line here. The blue line here is your 0, 1 loss. Your magenta line here, or your violet line here, is your hinge loss. Right? Your light brown or greenish brown line here is your logistic loss. Your green line here is your squared loss. So in a single diagram, so when we have logistic loss, what do we get? We get logistic regression. When we have hinge loss, you get SVM. When you have squared loss, you get linear regression. Right? Just literally in one diagram, you have 3 models sitting out there. That's what I love about the loss minimization interpretation. Again, the loss minimization interpretation in a nutshell is this. Since we can't differentiate 0, 1 loss, let us approximate it with other losses. Right? One such loss is logistic loss. When we use logistic loss, we get logistic regression. When we use hinge loss, you will get support vector machine, and so on and so forth. Again, we'll see all these techniques in future chapters of this course.